So in our polar representation, this purplish line here is going to be defined by two quantities. One of them is just this distance d. This is the distance of the line to the origin, the perpendicular distance. It's the distance to the closest point on the line to the origin. And the second parameter, so that first parameter is d, and the second parameter is theta, which is just the angle that this perpendicular makes with the x-axis, or if you want, you can have it be the angle that the line makes with the axis. Doesn't matter. You just have to pick an angle. So basically what we have now is a polar representation of an angle and a distance. In such a representation, by doing just a little bit of math, you can basically see that the dot product of any point on the line xy, dotted with the cosine theta, sine theta location of this normal, is equal to d. There's a lot of ways to do it, but basically you can show that if you formulate it this way, that x cosine theta plus y sine theta equals d. So it's a lot. Not a lot. It's a little bit ugly. Well, it's beautiful if you like trigonometry. It's ugly if you like algebra. It's a little bit more ugly than the y equals mx plus b formulation, but it doesn't have this problem that any of our lines are ill-defined. This is a perfectly fine way of representing any line. You can have any direction you want. Theta can go however it wants to go, and you can go right through the origin. D can be 0, or it can get as big as you need it to go. One of the interesting things now is, if you take a look at this equation, if I know x and y, what I have left in terms of d and theta is a sinusoid, all right? Which is why we say that a point in image space is now a sinusoid in Hough space, and we'll see an example of that in a minute. See, before we had this beautiful duality of a point in image space was a line in Hough space, and a point in Hough space was a line in image space. Well, because we've introduced this cosines and sines, it's still a duality, but it's no longer just simply between points and lines. One other comment about this. There's a redundancy or an ambiguity here. Let me draw it to you this way. Here's d. So if d can only be positive, this line has to be able to spin all the way around. So theta would have to go from 0 to 2 pi, 0 to 360 degrees. But if d could be positive or negative, then theta only has to go from 0 to pi, or 0 to minus pi, depending on how you draw that. The idea is you'd only need 180 degrees worth of coverage. Which way you do it doesn't really matter. In our algorithm, we'll do it in a particular way. But there's just this trade-off between, if you let d go positive to negative, positive and negative, then it only has to go 0 to pi. In fact, you can restrict things even more. If you make this be the origin of your image, the top left-hand corner, if you're going to say that your line has to be within the image, okay, then that restricts even more because it has to cut off that quadrant, so theta and d are restricted even more. But these are just choices that you make in terms of how you code up the algorithm.